Right, today I will talk about the CMB power spectrum in the cosmology. The CMB is cosmological microwave backgrounds, which is coming from the photon decoupling in the early universe. So we know that the temperature is inversely proportional to the scale boxes, and the scale boxes will be decreased in the inverse uh, in time. So temperature is still very high still in the very early universe. So if the energy of the early universe is the more greater than the binding energy, the atoms, for example, the hydrogen atom binding energy for the electrons is uh, 13.6 electron volt. So such a regime does no neutral atoms. There are some of the plasma electrons and the nucleus. So photon cannot be the transparent. It has a similar scattering with electrons. So photon cannot be the just going without the scattering. But if the universe expanded, the temperatures will be cool, then the energy will be the less than such a binding energy, and especially the recombinations, which is the some proton and the electron makes a helium, and hydrogens, which is a hydrogen nucleus, and the electrons makes the hydrogens, which is a recombination process which occurs in the almost 0.3 electron volts scales of the early universe, and after that there will be some of the photons decoupling is possible in the early universe, and such a photons will be the expanders of the large photons, decoupled photons has the large depth because of the cosmological expansions. So it has a microwave wavelengths, and that is called the cosmological microwave backgrounds. And because the large scale structures mean that there are almost homogeneous and isotropy universe in the observation. So there is almost the same cosmological microwave background CMBs can be observed, not dependent on the time or whether an isotropy several angles. So there are almost the same temperatures of the cosmological microwave background CMBs can be observed. So there are some pictures from the Planck's rule, some various satellite of the CMB, but there are just very small perturbations. Temperatures of such a CMB delta T over the T is the proportion to the density perturbation delta low super low. So it is 10 to the minus 5 megapascal scale, almost a very large scale. So such as some of the perturbations coming from the density perturbations in the primordial universe, and you make the large scale structures, which makes the star or galaxy formation. I want to talk about this such as CMB temperatures, the perturbations, which is some of the CMB anisotropy. And it can be expanded in the spherical harmonics, and it includes the various informations through all universe. So we can note that we assume that the isotopes and homogeneous universe. So the results of the such as Simpson's upper all depth matrix, and we assume that also all the blue is, which is for the strong tensor. But in the general case, there are very small perturbations like that. There are very small perturbation delta G mu used will be saved here, and only the linear term we will consider that under such a vector perturbation and the tensor perturbation can be neglected. So we only consider the scalar perturbations in terms of the scalar field capital pi. And we know that such a density perturbations in the specific position and time, that if we make the Fourier transforms in the momentum space, and we can have signs in the perturbations, density perturbations in the momentum space at a specific time. And if average also of the such as momentum is density perturbation, especially the scalar speed perturbations. The average is just equal to 0 because it's random. But if we consider some of the two-point correlation function, then there will be the sum of the past spectrums in the specific mode case will be obtained. There's a similar regimes of the green functions for the two-point correlation functions. Such a fast spectrum can be expanded as some forms amplitude i's and some index and with the -4. There's also expansion of the fast spectrum. And such a density perturbations will be closed as the increasing sort of the universe. There will be some of the equation with the motion for the density perturbation goes given like that. Almost some oscillations equation. Projects will make the oscillations and the density make the exponent increasing. So there are just some equivalent point between the projects and the density induced gravity. And the such temperatures variation delta t sort of t can be expanded in spherical harmonics in spherical coordinate. So if there are some specific directions at R, and they can be expanded in spherical harmonics with the index of the R and M, there will be the coefficient will be P. So is equal to CMB anisotropy. And if we also find it with two-point correlation function for such a coefficient in the expanded with spherical harmonics, then it will be used that the CL because there are no arm dependence, only the R dependence in here. And the CL is related with the power spectrum. It's because it's almost similar formalism C of similar power spectrums from the two-point correlation function from the scalar field. Density perturbations in the momentum space, but in this case, there is expanded in spherical harmonics. So such a coefficient of the diagram is very well related to the first spectrum. And if we expand the CR in the function of R as a plot, and such a CR plus has various information in the primordial universe. For example, the positions of the burst bump is related with the curvature of the universe, and the height of the burst bump is related with the baryon density. And from the such CMB observations from the several satellite, we can find that the temperatures, the perturbations, and from by the expanded in the spherical harmonics, we can assign the A alarms coefficients, and by the two-point correlation functions, we can assign the such a shear, which is the power spectrums to related thing, and the expanded R has the various informations to the early universe.